All right, we're going to talk about the relationship between particles in a gas and how gases are described. And yesterday, you should have done an assignment that explored some of this information. And so the three different things that we talked about, or the three different properties that are discussed, are 1, pressure, 2, temperature, and 3, volume, right? So we were looking at the relationships between those three things. And to explain why it works the way it works, we're going to do this assignment. The behavior of gases concept map, this is what I want you to open. And we are going to discuss the theory behind gases. I'm going to zoom in on one part. So the way we use this is we look at one of the boxes and then read the word, so gases, and then go along the line and then go to the words that are on the line. So gases are described using the kinetic molecular theory. So kinetic molecular theory, which is abbreviated, amazingly, KMT. And kinetic molecular theory has 4 different assumptions which are listed below. So, kinetic molecular theory described by 4 assumptions. The first is that gases contain particles which are, and let's pull up a little applet to describe what they are like. So here is a sample of gas, and the particles in it are going to act like the particles in an ideal gas. An ideal gas is something that follows the kinetic molecular theory, the 4 postulates. It's like the perfection of gases. And you can mathematically describe them in easy ways if you use that. So what ways are these particles moving? Each particle is moving how? It's moving around. So we might say that that would be kind of like a random, right? Constant random. But they're also moving in a particular manner. Are they moving in circles? No, they're moving in a straight line. So again, we will write that too. Straight line motion. They're in random straight line motion. So that's the first assumption of the kinetic molecular theory. The second one is that these gas particles don't occupy very much space. If we were to take all these particles and put them down in the corner of this container, they wouldn't really take up much space compared to the container, right? Unlike a solids would fill up the container, packed right next to each other. The particles would be packed right next to each other. But for a gas, the particles are very far away from each other compared to their size. All right, so we say that gas particles don't take up space. They don't occupy space or volume. You could say occupy space or occupy volume. Another thing that the gas particles are not doing here in this demonstration is that they are not attracted to one another, right? They're bouncing off each other, but they're not attracted to one another. And so that's the third assumption here. The gas particles don't attract to one another. What are they doing to each other? Well, and this is the last one. Gas particles, what with each other? What do they do with each other? Hit, or the word we use is collide. They collide with each other. What else do they collide with? The walls, right, the sides of the container. With the sides of the container. And these collisions may result in the transfer of energy, all right? But there's no net loss of energy. And so if we look at this demonstration again, what does that mean exactly? Well, each of these particles, because they're moving around, has some energy, right? And if we were to take the energy of all the particles and add them up, notice that when we started this, there was only one particle moving. I'm going to keep restarting this so you can see it's just moving. That particle has some energy, right? Once it hits another particle, it loses some of that energy, and some of the energy is transferred to the second particle. And eventually you've got all these particles moving around inside this sample. But if you were to add up the energy of all those particles, it would equal to the initial energy of this first particle. That particle there has all the energy that will ever be in this system. So once they start moving around, the energy doesn't increase at all. All those particles have the sum of all their energies add up to that initial energy of the first particle. So that's the fourth assumption of the KMT. So kinetic molecular theory describes gases, gas particles, and how they move. We call that an ideal gas. So ideal gases in which the particles obey the kinetic molecular theory. And so now I'd like you to go back to this our schedule, and you're going to complete this assignment, this first assignment, which will not take you very long. And then we will continue to fill out the concept map after that. All right, so I've told you what an ideal gas should act like, and that's according to the kinetic molecular theory and those four different things. But gases in the real world are not ideal gases. They're real gases. So they don't follow the kinetic molecular theory perfectly because they actually exist as real gases. And real gases do occupy space, and they do attract to one another. However, there are some conditions that exist where a real gas will behave like an ideal gas, and this is under certain pressures and temperatures. So I like to do the temperature one first because it's easier to understand. Should the temperature be high or low so that the particles do not attract to one another? So what happens when you cool a gas down? Here we've got a solid sample. I can heat this up, and the sample will become a gas. And the farther away we are from the boiling point, which for neon is I think like 27 K, and now we're up to 60 K, they are not being attracted to one another, right? So if I get the temperature very high, the particles will not be attracted to one another. And that's what we want. We want the particles not to be attracted to one another so that they behave like an ideal gas. So we say the temperature is high, and they will not attract to one another, and they will be following the kinetic molecular theory, this third assumption of the kinetic molecular theory. Now, when will particles occupy more space? When the pressure is high or when the pressure is low? Let's put a couple pieces, let's put some stuff in here. All right. So the pressure right now is like 17 or whatever. All right. How can I make these particles occupy less space compared to the overall space? What can I do? So if I expand this, now they're spread out, right? And they occupy less space as a percentage of the entire container. If I want them to have less space so that they don't occupy space according to the kinetic molecular theory, I want them to act like an ideal gas. So in order to make them occupy less space, I should have the pressure be low. Because if I make them occupy a lot of the space as a percentage, right, then the pressure is higher. This pressure is like 12 right now. But if I spread them out, now the pressure is like 3 or 4. If I want the real gas to behave like an ideal gas in which they don't occupy space, I should have the pressure low. You can also see that the pressure would be higher if we increase the number of particles. That would make them occupy a lot of space too, right? Get the pressure high enough. And if I squeeze the lid, see it popped the lid off, the pressure went too high. So when does a gas behave like an ideal gas? You want the pressure to be low and the temperature to be high. Let's follow this line that comes out of this kinetic molecular theory box. Kinetic molecular theory helps explain the inverse relationship between volume and pressure. Inverse means that they are opposite to each other. So as volume decreases, the pressure increases. So here's our pressure at about 16 or so. If I decrease the volume, the pressure goes up. Let me show you what the graph of that would look like. The pressure volume graph, this is one that you do have to kind of know. So if the volume goes up, the pressure decreases, and it looks like this. It's actually a curve. It's not a straight line. So in this video, let's explore the relationship between volume and pressure. I have the end of this syringe capped, and if I push on this plunger and make the volume smaller, I increase the pressure inside. I know the pressure is greater inside because if I let go, it will automatically move out. High pressure moving to lower pressure of the atmosphere. Again, if I decrease the volume, the pressure increases. I really have to hold this tight. And if I let go, it will go back to normal. That's an inverse relationship between volume and pressure. The direct relationship is between temperature and pressure. So if I increase the temperature, the pressure will go up as well. So let's put a couple of these in here. I'm going to increase the temperature, and you will see the pressure starts to climb. All right, so that's a direct relationship. And the graph for that would look like this. As we increase the temperature, the pressure goes up, and that is a straight line. All right, let's explore the relationship between temperature and pressure of a gas. So this flask is full of a gas, air, and I'm going to heat up those gas particles so that they are moving very quickly and move away from each other. Put in boiling water here. And then I'm going to cool those particles down so that they come closer together. When they come closer together, that reduces the pressure. The pressure gets smaller, as long as I have the flask sealed, which I'm going to do with this hard-boiled egg. Then I'm going to cool down that gas very rapidly in this snow, and let's see what happens to the hard-boiled egg. The pressure is smaller inside. The atmospheric pressure pushes on the egg, and it goes into the flask. There's also a direct relationship between, and I don't have it on the concept map because it's not really commonly talked about that much. But the temperature, if we keep the pressure constant, the volume will increase if you increase temperature. All right, so if we look at this, we're going to keep the pressure the same. So you can see the volume, you can see it is expanding now. All right, let's look at the relationship between temperature and volume. So we're going to keep the pressure about the same. I have a syringe that's capped, and right now it's at about 0.25 ounces, and it's been in this cold slush. Let's put it into boiling water and see what happens to the volume. All right, that should do it. We can see that it expanded a little bit. It's not a huge drastic change, but it is a change. Finally, right here in this box, 2 samples of different gases have the same number of particles. So let's take 2 samples. I'm going to write out a box. This is sample 1, and we'll have a second sample, same size. Sample number 1. Sample number 2, and we'll put some particles in here, and we'll put particles in the other one, and you can even, these particles do not have to be just elements. You can have compounds, so this is a compound that's a gas, but in order for these to have the same number of particles, the volume in sample 1 has to equal to the volume in sample 2, And the temperature in sample 1 must equal the temperature in sample 2, and the pressure must be equal as well. Oftentimes, they'll use STP as the standard temperature and pressure, and they'll say the same volume will have the same number of particles. So let's go back over here, and we'll say the pressures, temperatures, and volumes are the same in each. So all you have to do is make sure that all of those things are equal in each one, each sample, and they will have the same number of particles. So now you've got another Google form to complete, fairly simple Google form to complete.